All right, so in our last explainer, we dove deep into turning AC into DC. But what if you don't want DC? What if you just want to, well, control the AC you already have? Today, we're going to pull back the curtain on a device you've probably used 1,000 times without even realizing it, the AC voltage controller. We're going to break down how this hidden tech works, from the dimmer switch on your wall to some seriously massive industrial systems.
So here's the game plan. First up, we'll get a handle on what an AC controller actually is. Then we'll dig into the simplest case with the resistive load before tackling the real challenge, inductive loads, like in motors. After that, we'll look at the messy side of things, harmonics and control systems. And finally, we'll see how this all gets scaled up for huge three-phase industrial power. Let's get into it.
So first things first, what is an AC controller? You know, it's one of those technologies that's pretty much everywhere, hiding in plain sight. I promise, once you see how it works, you'll start noticing it all over the place.
I mean, think about a standard light dimmer, right? You turn that knob and the light gets brighter or fainter, nice and smooth. Or what about a power drill? The more you squeeze that trigger, the faster it spins. Well, both of those are using an AC voltage controller. The whole point is to manage the amount of power flowing from the wall to the device. You're not changing the type of power, just how much of it gets through. Okay, here's the more formal definition. An AC voltage controller is basically a gatekeeper. It sits between a fixed AC source, like your standard wall outlet, and a load, and its job is to deliver a variable amount of power. It does this by changing the RMS, or the effective, voltage. Now, here's the really key point. The frequency stays exactly the same. If you've got 60 Hz coming in, you've got 60 Hz going out. We're just chopping up and reshaping the waveform, not changing its basic rhythm.
So, how does it do this chopping? The secret sauce is a technique called phase control. We use a couple of super fast electronic switches called thyristors. Now, as the AC sine wave starts its cycle, we don't just let it pass through. No, we make it wait. We introduce a delay, which we call the delay angle, or alpha. Once that specific delay time is up, we fire the gate of the thyristor, and boom, it snaps on. For the rest of that half cycle, the output voltage just follows the source voltage. By playing with how long that delay is by changing alpha, we get precise control over how much of that waveform makes it through. More delay, less power. Less delay, more power. Simple as that.
Okay, let's really get into the weeds and analyze this, starting with the absolute easiest case you can imagine, a purely resistive load. Just think of something like an old-school incandescent light bulb or a simple heating element. These things don't store energy. They just convert electricity directly into heat and light.
Whoa, okay, don't panic. I know this equation looks a little intimidating, but the idea behind it is actually really straightforward. The only thing you really need to pay attention to is that alpha right there. That's our delay angle. See, the output voltage, VRMS, is totally dependent on it. If we set alpha to 0, meaning no delay, this whole big equation simplifies and the output voltage is the same as the source voltage. We get full power. But as you increase alpha, making that delay longer, you're subtracting a bigger and bigger piece from inside the equation. That makes the final output voltage go down. If you crank alpha all the way to 180 degrees, the output drops to 0. This direct mathematical link is what makes your dimmer switch feel so smooth and responsive.
All right, here's a question that trips up a lot of people. In basic AC theory, we learned that for a perfect resistor, voltage and current are perfectly in sync. That gives us a beautiful power factor of 1, right? Maximum efficiency. So, since we're using a resistive load here, the power factor should be 1, shouldn't it? Seems logical, but the answer is actually no.
And the reason why is so important? By chopping up that perfect sine wave, we've distorted it. It's not a pure sine wave anymore. You see, power factor isn't just about the phase shift between voltage and current. It's also about distortion. Because our waveform is now this weird chopped up shape, it's actually made up of the original frequency plus a bunch of unwanted higher frequencies we call harmonics. These harmonics are basically electrical pollution. They don't do any useful work, and they mess up the clean relationship between voltage and current. This creates something called a distortion power factor, which drags the overall power factor down. It's a fundamental rule in power electronics. If you change the shape of the wave, there are always consequences.
Okay, so we've got resistors figured out. But let's be real. The world runs on things like motors and transformers. It runs on inductive loads. And as soon as we swap out that simple resistor for an inductor, well, things get a whole lot more complicated.
This table really nails the key differences. For a resistor, the moment the voltage hits 0, the current stops. Dead. The switch turns off. But an inductor is different. It stores energy in its magnetic field, and it absolutely hates changes in current.
So even when the source voltage crosses zero and goes negative, the inductor's collapsing magnetic field acts like a battery and keeps forcing current to flow. This is huge. It means our thyristor switch doesn't turn off when the voltage hits zero. It stays on, conducting, until the current itself finally gives up and falls to zero. This changes everything.
And that brings us to a brand new term, the extinction angle, which we call beta. So, if alpha is the angle where the switch turns on, beta is the angle where the current finally dies out and forces the switch to turn off. The total time the switch is actually on is called the conduction angle, and it's simply beta minus alpha. With a resistor, beta is always a predictable 180 degrees, but with an inductor, it's always more than 180 degrees.
Now, this whole current lag thing creates a tricky design problem. Remember, we have two switches, one for the positive half of the wave, one for the negative. With an inductive load, it's possible that the first switch is still on when it's time to turn the second one on. If you just send a tiny, short pulse to that second switch, nothing will happen because the first one is still conducting. So the solution is to use a longer pulse, or even a whole train of tiny pulses, to make sure that second switch gets the signal and is ready to fire the very instant that first one finally turns off.
Okay, we've established that these controllers create these messy waveforms. So how do engineers actually analyze all that distortion? And maybe more importantly, how do you build a stable control system that can actually react and perform properly with all that mess going on? This is where we get into some really cool advanced techniques.
This chart is a great way to visualize a concept called the Fourier series. It's a powerful idea that says any repeating wave, no matter how weirdly shaped, can be broken down into a bunch of simple, clean sine waves. Our chopped-up waveform has one main component at the original frequency, the fundamental. That's the part doing all the useful work. But then it also has all these other sine waves at higher frequencies, the harmonics. And these things aren't just useless, they're actively harmful. They literally cause motors to vibrate and hum, which creates wear and tear. They generate extra heat that can cook the insulation on windings, shortening the life of your equipment. It's just bad news all around.
Fourier analysis is fantastic for looking at a system that's just humming along in a steady state. But what happens when things change fast, like when a load suddenly gets heavier? To model that, engineers use advanced methods like state-space averaging. It's basically a clever way to create a simplified mathematical model by averaging the system's behavior during its on-time and its off-time. This model is absolutely crucial for designing the feedback control loops that keep the whole system stable and responsive. Without this, you're just flying blind, and your controller could easily start oscillating or just fail completely when faced with real-world changes.
So far, we've been talking about single-phase power, the kind you find in your house. But when you get to serious industrial applications, we've got to scale everything up to three-phase systems. And this is where AC voltage controllers become absolute workhorses, controlling massive motors and even helping to stabilize the entire power grid. You know, three-phase systems have a really cool built-in advantage. In a balanced system, some of the most troublesome harmonics, called triplets, like the third and ninth, they just naturally cancel each other out, so your power quality is better right from the get-go. Two huge applications you'll see are in motor soft starters, which gently ramp up huge motors to prevent those massive inrush currents that can trip breakers, and in something called static VAR control. This is where utilities use giant versions of these controllers to fine-tune reactive power on the grid, helping to keep the voltage stable for everyone. Wow, okay, we have covered a lot of ground here, all the way from a simple dimmer switch to grid-level power electronics. Let's just take a second to recap the absolute key takeaways. So, what have we learned? AC controllers change the effective RMS voltage, but they leave the frequency alone. The magic happens through phase control, using that delay angle, alpha. When we bring in inductive loads, we have to deal with a new player, the extinction angle, beta. And remember, this whole process of chopping the wave creates nasty harmonics and hurts our power factor. But despite all that, these devices are absolutely essential for critical jobs like starting huge motors and keeping our power grid stable.
Okay, now it's your turn. I want to make sure these explainers are hitting on topics that you're genuinely curious about. So where should we go next? Should we look at cycloconverters, which can actually change the frequency of AC power? Do you want to do a really deep mathematical dive into Fourier analysis? Or maybe see how these advanced state-space models are used for DC to DC converters? Let me know in the comments which of those sounds most interesting to you. Or, hey, if you have another idea entirely, suggest it. Also, if any part of this was confusing, or if you just have a question, ask away. I read all the comments, and I'll do my best to get you an answer. And finally,
If you found this breakdown helpful, if you learned something today, the single best way you can support this channel is to subscribe and hit that like button. It honestly makes a huge difference and lets me keep making more deep dives like this one. Thanks so much for your time and curiosity, and I'll see you in the next one.